I'm going to draw a couple pictures up on the board and see if you guys will remember how to analyze these situations. Pretty sure you will. First one, we're going to say object number 1 is moving towards object number 2. Object number 1, by the way, is going to have a velocity of 10 meters per second. It's heading towards object number 2 with a velocity of 0 meters per second. We're going to say they collide and they stick together. Okay, so let's say that they stick together here. How would I analyze that problem? If they stick together, I want to analyze the collision between them. What would I do? What's the basic problem-solving technique that I use? Collision is what we just checked our work on, right? Conservation of momentum. We'd say PI equals PF. We'd say M1 V1I plus, what's the momentum of the second one? 0 equals MVF, or you could say MT times VF, right? The total mass, if they stick together, times VF. Now, if they didn't stick together, then we just say M1 V1F plus M2 V2F and so on, right? Wouldn't be any harder, really, just an extra term. You guys comfortable with that? Listen, if you got those 4 questions that we had on our practice question set number 4, you guys are comfortable with that. Okay, the homework questions from the worksheet that we did last week, okay, then you guys will be comfortable with this. Let me try another one here. Let's say this time, okay, object number 1 is at rest, and this time object number 2 is moving down towards it like this at a velocity of, let's say, 15 meters per second. They're going to collide, they're going to stick together, and they're going to head off as one object. How would we analyze this? Same way, right? We'd say PI equals PF. We'd say this time 0 for object number 1 initial momentum plus M1 V1, sorry, M2 V2I equals MVF. Agree? Good? No issues there, right? We could solve either one of those problems if we had enough numbers, like masses and so on, to sub into there. What about this, though? What about this one? What if we have object number 1 that's heading this way with a velocity of 10 meters per second, and we have object number 2 that's heading this way with a velocity of 15 meters per second, and they collide at this point right here, and then they head off together as one somewhere down here. How would I analyze that one? Yeah? That's exactly it. Yeah, exactly it. You do the exact same thing as we just did. Okay, listen, I didn't tell you this last week when we learned to do this, but when you solve conservation of momentum problems like this, what you were really doing is solving an X component, a horizontal component. When you solve problems like this, what you were really doing, although I didn't tell you that, was solving a Y component. What you're going to do now is solve both, the X component and the Y component. Okay, this problem that you see down here is the blue problem, and it's the green problem. So what you're going to do is break it up into both of those problems, the X and the Y. Now, watch what I'm about to do here. To solve the X component, the blue one, I'm going to do this. I'm literally just going to paste the exact same thing down here. The exact same thing. Like, I didn't even rewrite it. I pasted the exact same thing. Can anybody explain to me how I can say V2I is 0? Like up here in the blue problem, problem number 1, I said V2I was 0 because it was clearly at rest. How is it that down here I can say V2I is 0? Yeah, right? Good, because it's not moving horizontally. It's not moving on the x-axis. It is moving, but that's a problem for the y-axis, not for the x-axis or the x component. Okay, let's take a look at the y component now. You can imagine what that's going to look like. Take everything that we add up here on the y component and just move it down here. Can anybody tell me why object number 1 has 0 momentum this time? It's moving. Like it's moving at 10 meters per second, right? Why does it have 0 momentum, Bruce? because there's nothing on the y-axis. What you got to do here is be careful that you pick one axis at a time. Whatever's not moving on that axis is 0. I don't care if it's moving. It's got to be moving on that axis to be called something other than 0. So when you're analyzing this problem at the bottom, just do what you did last week. Just do it twice. Solve the x problem as if the green one doesn't even exist. Then solve the y problem as if the blue one doesn't even exist. Now, typically what you're going to do here is end up solving for VF, right? VF for the x component and VF for the y component. Now, I'm going to ask Julia again here because she was the one that basically told me what to do here. I know she's going to know what to do next. What do you think I'm going to do, Julia, with the x component of VF and the y component of VF? Yeah, do a triangle, a vector diagram, right? We know that the x component is this way, whatever we solve for that to be. We know that the y component is going to end up being this one, whatever we find that to be. And then we're going to find the final velocity, including the angle, by doing a little bit of geometry and trigonometry, right? The final speed will be equal to this. A squared plus b squared is equal to c squared. And then the angle will be found by taking the inverse tan function of opposite over adjacent. Is that ringing a bell? Is that ringing a bell to you from Physics 20? Right. This is what we're starting today is two-dimensional collisions, two-dimensional conservation of momentum. It's not really different from stuff we've already done. If we combine what we did last week, i.e. the blue and the green, separate from one another, if we combine that with what we did last year, and that is the vector analysis and finding a resultant vector by having an x and a y component, then we're done. So don't do anything new here. You don't need to learn anything new at all today. Just combine what you learned last week with what you learned last year, and you should be good to go. Let's take a look at your first example that's on the sheet that I handed out to you a little while ago. It says a 1,200 kilogram car traveling north at 10 collides with a 1,500 kilogram car traveling west at 12. The two cars entangle. We know what this means, right? We've seen this before. They head off as one. What's the velocity of the wreckage immediately after the collision? So let's say car number one that has a mass of 1,200 kilograms and a velocity of 10 meters per second to the north collides with car number two, which is moving to the west. It has a mass of 1,500 kilograms and a velocity of 12 meters per second to the west. Where do you think they're going to go? Where do you think they're going to head? The rough vicinity, right? We don't know exactly, right? But Bruce? Yeah, somewhere up here northwest, up and to the left. Where exactly? Well, we'll figure that out, but we know they're going to go somewhere up there because if we have a north momentum before the collision, we have to have a north momentum afterwards. If we have a west momentum before, then we have to have a west momentum after. Okay. Let's do x components. Pi equals Pf. We're going to say the momentum of object number one. The momentum of object number one before the collision is what? 0, because it's all on the y-axis and we're only analyzing x, right? The momentum of object 2 afterwards is m2 v2i, and then combined it's going to be mvf. Now, even afterwards, it's not completely x component, right? But we know at least part of it is x component, so we can't get rid of that term. m2, 1,500 kilograms, we're going to say times negative 12 equals 2,700 kilograms times V. Gives me VF. That is X component is negative 6.66667 meters per second. Now the Y component, once again, PI equals PF. The momentum of object 1 is M1 V1I. 1,200 times 10, right? Harrison, what's the momentum of object 2 for the Y component? 0, because it's all on the x-axis, right? We want y-axis. Object number 2 isn't moving on the y-axis, so we're going to just assume that it's not even moving at all as far as we're concerned right now. MVF, we're going to say 1,200 times 10 equals 2,700 times VF. And we're going to solve for VF here. 0.81481. Good. All right, let's combine them now. Let's say X component is 6 point, is that right? Are those numbers right, guys? It seems like it might be off because there's such a difference in the numbers. For this one, 4.44. Let me just double check that here. 1,200 times 10 divided by 2,700. Yeah, 4.444. So what kind of alerted me to the fact that that might be a wrong number is the fact that I had 6.7 up here and 0 point something down here. It could happen, but in all likelihood, those numbers are going to be closer to each other than what we had there, right? So that alerted me that I might have a mistake there. It didn't tell me for sure that I had a mistake, but it was at least enough for me to check my work because the numbers were so different there. So we got 6.6667 right here. It's to the left because it's negative. And then we have 4.44. It's upwards because we know that it's positive on the y-axis. We're going to solve for V right here, and we're going to solve for theta. Solve for V using the Pythagorean theorem. 4.4444 squared plus 6.66667 squared. Square root that. We end up getting 8.01. And theta is the inverse tan function of opposite over adjacent. Make sure you're in degree mode here. Second function, here, let's do this because some people have a little bit of trouble with trig here. The inverse tan, theta is the inverse tan of opposite over adjacent. Opposite is 4.44 over 6.667. So we're going to say it is, I get 33.7 degrees. And that would be north of west, 33.7 degrees north of west. By rights, actually, how many significant figures should we have? 4, 4, 2. Final answer should be 2 digits, right? So we should, by rights, say that this is 8.0. And this is 34 degrees north of west. Is that okay? Is this any harder? Well, sometimes when we put things together, it does seem to be a bit harder. So don't think of it as being together, right? Think of it just all separate, right? Think of this green problem right here, the x component, as just a problem that we did last week with object number 2 at rest. Then think of the blue problem, the y component, as a problem we did last week with object number 2 at rest. And then once you get VF for both of them, then just combine them. I'd like you to take a look at worksheet number 4 now, please. Right now, only questions 1 to 3. There's more questions on the page, but right now, I want you to stop at question number 3 if you happen to get that far.